And with the standard model we now have, we've now, according to the sort of rules of physics of what counts as an observation, everything has now been observed in the standard model of particle physics, or are we still waiting to see anything?
Everything in the standard model has been observed, that's correct.
So what are the things that you as a particle physicist are hoping to be observed? So, because the interplay between theory and an experiment is interesting. So the Higgs boson was predicted sort of 50, 60 years ago and finally is observed. What things are you currently as a theorist excited about? Maybe not now, but maybe.
What I will be excited about is anything new, anything that disagrees with the standard model. So for sure, I'll be jumping on that and working on it. But for me, the current, it's tantalizing. The new particles are being a bit late to show up, a bit later than we think, actually. So there's this theory called supersymmetry, which I've worked on a lot, and it predicts lots of new particles, and it explains some mysteries about the Higgs boson that we don't currently understand. So it seems like a really beautiful theory, and when you really understand it, you feel in your heart of hearts, this has to be right, or a lot of us do, not all of us do. And I do, but yet the Large Hadron Collider hasn't seen these new particles yet. So I'm kind of still expecting them to show up, but they're late to the party, it's got to be said.
So you thought you would have seen them by now in the run of the LHC?
And many of us did, yeah.
But there's still a chance that they'll appear in the next run?
There is, but it's diminishing because we've done quite a lot of collisions now at the Large Hadron Collider. And we're reaching this limit of diminishing returns where you've already looked, around your house for the phone in all the obvious places, and now you're having to look under the fridge, and it's getting less likely each time. So the only way to make a big leap forward and really search your house completely is to increase the energy, and that won't happen for a good few years. Yeah.
Given that supersymmetry, to you and to many physicists, has the feel of a correct description of reality, what kind of evidence does it take to, because maybe it's easier to prove something is there, what evidence or observations do you need to change that that belief?
That's an interesting question in the case of supersymmetry, because basically what you do is as you run the Large Hadron Collider and you don't see these things, you say, well, they've got to be heavier than such and such, because we didn't see them, otherwise we would have seen them. And then you run a bit more and you're like, well, actually, we move that up a bit. And the thing is, the heavier you make these particles, the less you solve the problem of, the less you solve these mysteries to do with the Higgs boson. But it's a fuzzy thing, and taste plays a role. At some point, they're too heavy and they don't solve this aesthetic problem that we have with the Higgs boson, and you give up. And many people have. Many people have said, oh, look, we were just wrong. My feeling has gone for supersymmetry. I don't think it solves the problem anymore. Some of the rest of us think that's premature. I think there's still a chance. I don't know. This is an unanswerable question. Yeah. So at the moment, with supersymmetry in particular, it's like that. With some things, it depends on the theory. With some things, it's sharper. Yeah. You can definitely disprove it.
So is this a particularly exciting time in particle physics? Because it sounds like the interplay between theory and experiment is quite quick and close at the moment, whereas perhaps 50 years ago, they had to wait. They just played in the world of theory for a long time. Is that sort of a?
I think the opposite is true.
Oh, okay.
So last century, there were these surprising experimental results coming in, and then if you're a theorist, you're scrabbling around going, oh my God, what does this mean? We've got to develop new theories. So personally, I'd like that. I'd like to be in that. It's a bit frenetic. It'd be quite stressful, yeah. But I'd like to be in that era. Whereas now we've had, dominance of the standard model. It's been tested. It was invented, in the 60s. Some 50 years ago, and it's just passed every test.
Yeah.
Bang, 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 bang. We've been testing it more and more accurately and in many more different situations. And many see that as a success, and in some sense it is. It's an amazing, theoretical construct that has proved to be correct so far. But if you're working on the next thing, like the cutting edge, like I am, really you want something new to get your teeth into. So now theory kind of has outstripped experiment. We've gone far ahead in the future in terms of the theory. We're saying, we could have all these new particles from supersymmetry, or it could be like this or like that. Let's go and look for them. This is how you look for them. That's one of the things I do. But I think the other way around, where experiment is really informing us as theorists rather than theorists telling experiment, go and find the Higgs boson. It's predicted again in the 60s. This is how you look for it, etc. I mean, it's all good work, but just in terms of working in the field, for me, it'd be more exciting the other way around.
Is there any things that, with the current LHC, the current collider, we're unlikely to be able to detect just because it's not going to produce enough of those sorts of collisions?
Sure. So there are lots of theoretical ideas about new particles and forces that may be around. And we don't know if they're true. They're all speculative ideas. There might be good reasons for believing in some of them. It's a matter of debate and argument. But you're only sure once you've seen it at the Large Hadron Collider. But some of them, the particles are just too heavy. You haven't got enough energy at the Large Hadron Collider. You're always turning energy into mass at the Large Hadron Collider and vice versa. And so you need, in order to produce the heaviest particles, you need more energy. But the Large Hadron Collider only has a certain amount of energy in it. So you could only produce something that's, say, about 6.5 times the mass of a proton. Sorry, 6,500 times the mass of a proton.
That's the heaviest thing you can
That's the heaviest thing you can produce there, more or less. So if you've got something new, which is, 15,000 times, there's no way you could see it. So you'd have to build a new collider with more energy. And there are plans to do that. I don't think we've acquired the funding yet, but yeah.
If part of your work is to think of what ways to detect these new theoretical particles, is it, so the LHC is obviously a huge, massive international project because of the size and the cost of the thing. Is that whereas, in the 20th century they could make these discoveries of new particles in labs, is that now a limit to, the sheer size and cost of the experiments required to test new theories? Will they always be so enormous?
With current technology and extrapolating that technology, yes. It costs like $1 billion, £1 billion, or something like that in order to run one of these big experiments. It involves, tens of thousands of people. So, but that for the foreseeable future, unless there's some major technological breakthrough where you can get huge energies out of some other technology, totally different technology, then it looks like, that's going to continue. And so that is now the sticking point with making a higher energy collider. You need to get some countries to get together and all put in some money into the hat, a few $100 million each or something, and say, right, well, we're going to build it, and we're going to build it here and get everyone to agree. That's quite a politically difficult thing to do, especially if you're just exploring and you say, well, we don't really know what we're going to find. Like with the Large Hadron Collider, we knew indirectly from other data that even if the theory was wrong, something like the Higgs boson had to be there in the right kind of mass for the Large Hadron Collider to see it. So there were still people who didn't believe in the Higgs boson back in the 80s when it was conceived and set up. But we had this kind of no-go, no-lose theorem that we sold to the politicians, which was true, which was we'll find the Higgs boson or something like it with this machine. And at the moment, actually I'm working on a no-lose theorem for the next collider, but it depends a bit on some tentative data that's coming in, and it hasn't quite reached the 5 sigma, this 1 in 10 million chance yet, but it's over the 1 in 1,000 chance, so it's kind of interesting. So what we're saying is, look, if this data gets stronger, then we've shown by studies of a future collider that it's a good idea to do it. And if the evidence gets weaker and it just turns out to be a statistical fluke, then we say, okay, that motivation has gone away. But it's at least a kind of scale for measuring, when you're talking to a politician, how useful your future collider is going to be.
So there's political and economic limits on observation.
Oh, very much so. Because also this collider is going to be hosted somewhere, and a country might think, we want it hosted in our country, we'll put in a bit more money. But some countries say, well, we don't want anyone from outside. Our scientists are good enough on their own, which is not the case. You really need a worldwide collaboration. This is ultra specialist, cutting edge stuff. And you need the best scientists from all around the world to really to be able to push this forward, I think, and many others think. So yeah, it's a big political discussion.